I'm a technical consulting engineer for HPC, and I will present here you the Intel Advisor tool. So two specific aspects of this tool, the offload, modeling, and analysis. I hope the screen is large enough. So, okay. So actually, the Intel Advisor tool, it evolved over time. It is a kind of a multi-tool. Initially, it started as a tool for thread prototyping years ago. And so then I think very important was then the introduction of the vectorization optimization in it. So it's a very good analysis where you can vectorize or what is the quality of the actual vectorization in your code. And then it got, I think, a little bit famous about the integrated roofline analysis. Also was added some analysis for some opportunities to build heterogeneous algorithms with graph algorithms. Yes, and finally now we introduced the so-called offload modeling so that you can get an idea about how good your code would run with an accelerator. And for this, we also implemented the roofline analysis. And so let's start then. Here's an overview about the two aspects again regarding the GPU. So if you have the application, either existing CUDA code, which you then migrated with the Intel DPC compatibility tool, you go presented to some SQL code or existing C++, Fortran C, or also existing OpenCL application. For all these applications, then you can use the Advisor tool to do some GPU modeling and just to estimate how good it will run on a GPU. And then in the lower part, you see the analysis capabilities of the tool when your code is actually running on the GPU. Then you can do with the Intel Advisor, roofline, and flow graph analysis. And this is so the offloading, modeling, and roofline analysis I will show you in this talk here. So in principle, it starts now with the offload modeling slides, but I will switch now to the demo because I have to start some actions there, just because this takes some time and I will want to show you fresh values. So I'm now here on the Dev Cloud, and I use now here, I can, on the Dev Cloud, I have two opportunities. One is I can directly SSH into it, or I use the Jupyter Notebook, and this Jupyter Notebook, and here I selected a third analysis. You can use also the access with the Jupyter Notebook to open a terminal. I do this because when I connect directly with SSH, there are no GUI capabilities on the Dev Cloud, but with the Jupyter Notebook, I can at least show you HTML files, and this is sufficient, I think, for most of the part of this presentation here. And as Heinrich, I will also use an NBuddy example. But before I go on with this, I will show you one important thing. If you also do the same approach here as I do with the Jupyter Notebook and a terminal in it, by default, you will end on a node with typically no GPU included. So you can see this with the clinfo -l command. There is no discrete GPU. It's only integrated GPU here. But if you prefer to work on a with discrete GPU, you can still submit a job from here, and I will do this now. So I submit a job, interactive job, and go from this node into another node with a discrete GPU. Here it's the Iris Xe Max. Will take a minute or so and some seconds or so. So now we are in. The first thing I do is just to load the environment, because I need all the tools. So source, Intel, one API, set vars.sh just to load all the tools. As I showed you yesterday, you can also do it by using modules if you prefer to work with modules. And then I will go into the directory of the n-body example here. And here are the sources. Perhaps clear this a little bit. So here are the sources. And yeah, this is a simple n-body application here in the playbook. You see where I got it. So I do not provide the sources themselves. I just copied it from the net, yes, by cloning it there. And then I went into this directory with the best version. So it has this n-body goes through different optimization versions. And here for this example, then I select the best, the optimized version. And if we look into the source code here in gssimulation.cpp, so here is the important loop here. The important there's an outer for loop goes over the time steps. And then we have here the loop. This is a molecular dynamics application, the n-body, and typically then it runs over the particles here. And this is a loop over the particles. It's parallelized with OpenMP, and it is also optimized for vectorization because it goes over these particles with in blocks, the tile size, and the tile size is then used. Here the tile size is set to 8, and the tile size is used for vectorization. Therefore, we have here now this inner vectorized loop over the tile. And yeah, and here then the actual particle calculations. The loop is also vectorized. Then we have for the symmetry, we have here then the other calculations. And finally, we have here the reduction operations, which is also very natural in molecular dynamics applications. And so I make the code, the executable, and then I just want to show you that it's actually running with OpenMP. What is it? I run it with 64K particles. And here you see with the KMP affinity verbose flag that the threads are that 24 threads are running on this system. So the default set is the number of cores, and so it's running here on the Linux threads, which are mentioned as OS procs here, and there's no special bounding, so they can move around in principle. Then we can also fix them to the cores by just adding here the scatter argument. Now they are already bounded to specific processors, to specific hyperthreads. So I set then this variable as a default, the scatter. I export it to make it easier. And run n-body again. And then you see here, what we see is about 1.1 teraflops of performance on 24 threads. Okay, then the question is, what can we expect from running on GPU? And therefore, I just then in this playbook, I then take this command here, which I will explain later in the presentation, and I just copy paste it and let it run. And now it started. Okay, back to the presentation. So what will be the outcome of this? And we will see it later live, and then I will modify it a little bit. So what we do is that from an optimized binary, and therefore I selected this version 8 of the n-body code, we run it on a CPU, and then the tool helps us to define interesting sections, which probably could run well on a given accelerator. And it also it identifies these loops, and it also does a performance projection on the accelerator. And this will be then presented in different views here. And one view is here, what is the overall expectation of this for the speed up. And here we see in this example, we had some code, some parts of the code were run on the accelerator, part of the run, try this. Part of the run here, this is the time on the host, this is the time on the accelerator. And for the accelerator, we have a speed up for the accelerated code of 8.9. And by Amdahl's law, because still parts of the code are running on the host, the Amdahl's law speed up for this example is calculated to be 8.5. Okay, then I cannot move it again. Okay. So for this modeling, we have different opportunities. So one is, as explained, that we start from measurements on the CPU. So we see C++, Fortran, or Python code, but also we can use it with DPC++ code and OpenCL code or OpenMP code. If we select the target host for this measurements, and then we get a projection for the same CPU, for the identical CPU, plus some estimation for GPUs, which could be existing GPUs, but also future GPUs. For example, if you just know or not believe to know some performance matrix of a future GPU. And what we can also do, we can do real measurements on a CPU plus a GPU, measure there with DPC++, OpenCL, or also with Offload OpenMP, and then we get a projection for a CPU plus acceleration on another GPU, on a future SPU or a different GPU in the market. Okay, what is the technology here behind it? So the execution time on the baseline platform is taken on the CPU. And then from this, there's an estimation done for the compute time on the accelerator. And also an estimation is done for if a code is bounded by cache and memory. So this is important then to do an estimation for this movements from cache and from memory or from to memory. And what we have also in addition is a so-called offload tax estimate. So this is one thing is here the data transfer. But also the invocation of the kernels gives some additional tax. And then this is then the principal formula for the overall time, so that we take the maximum time just from the compute and the memory subsystem, and add there the data transfer and also the invocation, and this gives then the estimated time on the target device, on the combined run CPU plus acceleration on the GPU. And clearly, this is only profitable if the accelerated time is smaller than the original time, and otherwise it's too much overhead, and acceleration by the GPU will not pay off. And by this, we then find good candidates here for offloading and bad candidates for offloading. And also there is also information what are the reasons for the workload, what it is bounded by, and this may give them the reasons why some candidates are bad. So it could, for example, here in this example, it was a last level cache bounded. And here you see also that sometimes it's not profitable, therefore, for different reasons, to accelerate a loop. Yes, sometimes it's just, in principle, it would be profitable, but just the time is too small. Could be one reason. And then we can also go deeper into this analysis by clicking and selecting certain loops. Then we'll see a snapshot from the sources and got a lot of information about the timings, the total time, the time on the accelerator speed up, then the offload text, so the data transfer, and the trip count of the memory, the traffic, so to the different levels of memory. Yeah. As mentioned, so here there are details about to which aspect a code is bounded. It's also then shown in more detail than in this so-called grid information. For this code, 95% of the workload was bounded by level 3 bandwidth, but it can also appear that the several bottlenecks will show up. Yeah, and also we can then see information about the data transfer, and this goes down then to the source code. And for the source code, we can identify the different memory objects. Typically, these are then the source lines where these memory objects are allocated. Yeah, and as mentioned already, there might be different reasons why a kernel should not be offload. So one very important aspect is obviously dependency issues, but a dependency issue, yeah, what we know it already from CPU dependency issue prevents vectorization, but it also prevents then threading, so parallelization. There are exceptions from this. If the dependency is in a very short range, then it might be still possible to do some vectorization there, and then also it should, but it's difficult. You have to guide the compiler if you will want to overcome such short range dependencies. Yeah, it could be also that the code is not profitable because total time is too small to the trip count. Yeah, related also to the trip count. And it could also be that you can compare the acceleration on different GPUs, and this might also then change the picture. So, for example, here on a Gen 9, it was not profitable to offload the kernel, but then if we change here to a Gen 11 GPU, the projection says that it should give you some speed up. So this makes it therefore interesting also to play with different accelerators in this tool. And I will show you how you can influence it, for example. What is also part of the advisor is that you can have such a view here of your the visualization of your call graph, but you need additional software, this .graphviz utility installed, but then you can visualize your code in this way. What is a prerequisite for using Offload Advisor? So one thing is you should request full debug information in the compiler and the linker. This is just also important to visualize and in the snapshots the source code. You should only request moderate optimization, so that the -O2, because otherwise the compiler might move around too many things, might move around loops, might split them, might fuse them, and then this makes then the analysis too complicated. The same is true for no IPO, so disable the interprocedure optimization because this might interfere with the collection of the performance data. And then we have three different ways to do the offload analysis and the performance estimation. Each of them depends can be consists of two steps. The first step is pure profiling, yeah, to collect data, and then the second step is do the performance modeling. And for the profiling, there are three different approaches to get an estimation. It's kind of most convenient to less convenient, but the same is less control to most control. So with most convenient, you just you just execute a Python script, this run OA, offload analysis Python script, as I did it just to start the example, which is a combination of A and B. Then you can split this in the profiling Python script collect.py and also the analyze Python script with B and for B, and this gives you somewhat more control already, and most control you have by executing the advisor itself. So what this is advisor is now our what was advisor XE command line in the past, but this is still available, but now I think it's more easy to just start advisor. Advisor will start the command line tool. Advisor -GUI will start the GUI, so it's more easier to remind. And then you have to start it multiple times to collect all the data, which is necessary. And then finally, you can do the analysis and the projection again with the Python script. Yeah, as I showed you, you will get a list of loops to be offloaded, the estimated speed up, and some more files, which you could in principle also use to do some own calculations if you're interested. And this is also nice for doing some batch processing. For example, you could do some regression testing here, set up a process for regressions also, that you can run over several, in principle, over several analysis. Yeah, so I use this Python script, and what is necessary here to have this environment variable APM defined. This is already defined if you just start the overall loading of the tools, as I did it with the setvars.sh. If you want to use just the advisor, then it's also set up if you just source the advisor script here, the advisor xe vars.sh. And then this environment variable points to the advisor installation directory, and there's the subdirectory performance models. And in this directory, all these tools are gathered. So you started with then advisor python.apm collect.py, and you provide a config flag here, which is for which GPU you want to do the projections, and then finally in the end of the command line you provide your application. Here it started with advisor Python. Is this important? In principle, not. You can use it with other installed Pythons. Yes, the advisor Python is only provided for convenience. Actually, I found that it requires currently it requires Python 3.6 or 3.7 and doesn't work with newer Python. So therefore, I used now in my scripts and in the playbook I used consistently advisor Python. Yeah. And then you run as a second step, you run the analysis. So I used here in this slide, I used the middle approach with the two Python scripts. And then you also can here specify the GPU and um, and then an output directory. So for the project's results. Yes. So this is different from this project directory. Project directory is where you gather all the collected data from measurements, and then in your project results directory, you will get the output files, the CSV files, but also an HTML report. You can merge it. For me, it's cleaner to have this separated. Yeah, here again mentioned the alternatives in starting the offload analysis. So this describes a little bit the technology behind the scenes. So an application compiled with -0.2, we will do this first. The survey run will be done, so which is also done for normal use of the advisor on a CPU. Then some markup policy will be applied. For example, I said that only the loops which are already threaded with OpenMP should be analyzed, because these are the interesting candidates for offloading. And if you do not do this markup, just the run takes longer. And then in the second advisor part here, in the second run, the flops are counted, the trip counts are, it does some dynamic instrumentation, and then it counts everything, the trip counts, the flops, it does a traffic simulation, it does an offload data transfer analysis, a binary static analysis, looks for dependencies if you don't switch them off, which I did also, because for OpenMP loops, I know already that there are no dependencies. And then in the analysis step, the performance models are applied and the output is generated. As mentioned, I choose to suppress any dependency analysis. Yes, because I know that there are no dependencies and in the OpenMP loops, and it will just cost more time and makes a and then you have to do also additional analysis. But as I said in the beginning, it's clear that any loop with dependencies is no candidate for acceleration, because these loops will also would in principle run on a GPU also sequentially, which makes no sense. Yes, you cannot offload them. And also for the analysis, and the assume parallel flag is added. Yeah, and selecting only OpenMP loops or other loops, you can also even specify specific loops. So the loops have identifiers, and there's a commands where you can get the information about the loops, which loop it is, and then you can specify specific loops, that only specific loops are projected onto an accelerator. But here the easiest way is just to say markup OpenMP, and then only these loops will be selected for the offload analysis. Yeah, the output is a report in HTML, which you can open in your browser. And then some other files. So there's the CSV files with all the data in it. Then the program tree dot and program tree dot PDF. This is just for this graphical for this visualization of your call graph. And some JSON and log files that are used to generate the HTML report. Okay, before we start with the second part of the talk here about the roofline analysis, I will switch now back to the actual run, and it has finished. As you can here see, it took 4.5 minutes to do the analysis, and I have now here 2 new directories. The advisor or offload. I selected the name, so here you can. Let's go back to the command. So you have seen it in the slide. So I selected here advisor Python, then the combined run offload advisor Python script, set some verbosity flag here, and this is the project directory, so where all the data is collected, advisor OA 64K. Then I mentioned here that I wanted to do a projection for the GAN 12 DG1. So this is the officially it's the ICE XE Max GPU, the discrete GPU. I also said I want only to see the OpenMP loops. I want to do only collect basics, which then switches off the dependency analysis, and then I have here specified the output directory. This is where the CSV files and the HTML file will end up, and then I specified the executable. All is you will see here in the playbook. You will find it in the playbook for your own experiments. Then the playbook says open the HTML file with the Firefox. Okay, we have no Firefox here, but as mentioned, it's easy. I can go there, wrong directory. I can go into this directory and find here the HTML file, and in Jupyter Notebook, I can open this HTML file. It's a little bit careful here. We have to select here trust HTML, and then it starts and it opens here. And what we see here, the speed up for the accelerated code would be 1.3. The number of offloads will be only 1. The fraction of the accelerated code is 94%. So we find these numbers also here in this table. The time on the CPU is 0.160, time on accelerator would be 0.8, and then this is a little bit surprising that it calculates here the under slow speed up also to 1.3. It would be necessary to see here more details, so more numbers behind the dot. Okay, here is the assumption about or what is in the model, in the projection model for this IRX-XE Max. So it was selected to run with 1.65 gigahertz frequency. There are 96 execution units on it. We have 16 megabyte L3 cache. Then the L3 bandwidth is about 634 gigabytes per second. Then we have here the GTY bandwidth, the bandwidth to the DRAM, and also the bandwidth for the PCI Express. Then it shows here that top offload, there was exactly one loop. This is the outer loop, I can tell you, which was selected for the offloading as a candidate. And there are more or less no non-offloaded loops. One is here the KMP create worker, so it's from the OpenMP library. And one in my first example, this didn't show up. It is some smaller loop here. The total time is too small for reliable modeling. Okay, one could use a different flag here to model also such small offloads. Good. What we can do here then, select this loop. And then here on the right, the sources will show up, and it's loop 12042. Yes, if you look into this again here, into the source code, this is exactly the outer loop here, the parallel 4 outer loop. Let's see the 196. Okay, this was a reduction loop. The reduction loop is it seems to be too fast, or was too fast here. But this is also an inner loop. I could not analyze this. Okay, because of short time. Going back to this, it starts from the beginning. This is just because of how Jupyter notebooks work. Okay, and then we can here, we see also a stack here. Very interesting that it found here that the square, the inversion of the square root, that it took most of the time in these loops here. It's also found. And then what we can see also when we move here around in the group, so we see elapsed time, there's a lot of details here. The estimated speed up 1.25, so it's a little bit less than 1.3, so and the second number is shown. Then bounded by compute, yeah, this is very important information. Estimated time after acceleration, total time execution by compute, and so on. A lot of information is shown then here. Some of the latencies, the offload taxes, the data transfer, kernel launch tax, global size, local size, the SIMD widths, and so on. A lot of information you can get here. Okay. It's no, I accidentally closed this because that now comes the next aspect I wanted to show you here in the what you can do in the HTML. You can change here the assumption about the architecture. Yeah, you can, for example, increase it to a larger frequency, or you can double the execution units, or you can double the bandwidth, and so. And then you can do a new projection. Normally, you can download this configuration file here, but this doesn't, it works in Jupyter, in Firefox, it doesn't work in Jupyter Notebooks. But we can have a look into this configuration file. And this is the configuration file. And here are the different possibilities where you can influence it. You can select a different tiles per process. You can select a different frequency, and then they can have here multipliers for the cache size, for the bandwidth. You can also have memory bandwidth, PCI link. You can influence it. So in Jupyter Notebook, you just can copy paste it and put it into a file and then change it, or you open it with Firefox and then download it, open it with Firefox, and then get the file from there. So I did this before, and I copied it from my backup. So backup, copy backup, scalars to here. And then kind of, so just looking into it, should be now visible here. Open it, yeah. Without VSI. So what I just then put here into this file, I said, okay, let's just do an experiment. I multiply the execution units by factor 2, and I multiply also the level 3 bandwidth, just as an experiment. And the command then to exploit it and to use it is then here, the time advisor Python again. And the important is here I do not only specify, I have here still the config gen12 dg1, but I also specify here the config scalars.ml so that I will scale this. Just take some seconds. Okay, it now has created a new output. I gave another output directory here. Here it shows up the result or scalars. And I open this report now. And hopefully it worked. Okay, and now the speed up for the accelerated code would be 2.5. Yeah, we have a very compute bound code, so then this is parallel, and therefore if we double the execution units, then also the speed up for the accelerated code should double. We have seen before it was in detail, it was not 1.3, it was 1.2.5. Now we are at 2.5. And the overall speed up would then be 2.4. Yeah. Okay. I did it with these scalars. Here's also a command where you can do it just by modifying the parameters directly. I started it, just showing it here. You set with a set parameter. Here are the set parameter flag, and where you can directly set the frequency, change the frequency, the U count multiplier, even 4 I selected here, the multiplier 5 here, and so on, memory bandwidth. So you can play around. In particular, if you know from Intel publications or you believe to know some number for some interesting future architecture. There's some presentations around where you can get some of these parameters. Okay, then going back to the presentation. What's the time? Okay. This is about the roofline analysis for the GPU code. And so what is roofline in brief? Mentioning, so in the roofline, it shows your architecturally performance limits. So perhaps if I have time, I will do some short recap in some slides. I have them in the backup. So what is the idea behind the roofline analysis? Just to show it here, you have some lines. The horizontal lines are typically these are the performance limits with respect to calculations, and then you have the diagonal lines, and which are the performance limits with respect to memory transfers. Both performance limits are expressed in gigaflops. These are logarithmic scales, and therefore these diagonal lines don't go through the origin of this graph. And these are absolute limits. So if you and then you have some we have some dots here, and these dots represent loops or functions. And the distance to these upper lines, they specify your performance headroom. Yeah, and so with respect to the horizontal lines, it's a performance headroom with respect to calculations. So can I improve it? You see here that there are performance lines for double precision vector add, double precision vector fused multipliers and add, and then single precision vector add and single precision fused and multiply. So it depends on which lines are important for your code, whether it's double or single. And then you see also here the lines for the bandwidths. So DRAM, then the different cache levels. There's additional yeah, for the different cache levels, either if you do a roofline analysis for the CPU or for the GPU, so then they will see different lines. And yeah, in short here, if you are in the right part with your loops, then the upper limit, yeah, the final limit is the calculation. If a loop is in the left part, then the final limit is some bandwidth. Yeah. For a specific loop, if the specific loop, you still have to cite what to do and what you can do, because also if a loop is in the lower part on the left, it's you still might have room for some calculation improvement. Yeah, it still might be that you are just running a serial loop, a scalar loop, and you still can vectorize it, which will move you up in the graph. Yes, it depends. As mentioned, you have these graphs are shown by default for all the different floating point sizes, so either single or double precision, but you can customize this view by deselecting certain roofs. There's a menu here, a small menu, where you can deselect it. You also see here in this menu, you see the numbers for the values for this peak performance and for this bandwidth. And these numbers, and this is very interesting and which makes the tool very powerful, these numbers are real numbers. So these are not numbers from paperwork. So the principal numbers, the absolute maximum performance, these are measured bandwidth. So at each run, if you do an analysis, then advisor will start some short running benchmarks and really measure these performance numbers. And this is therefore these are the numbers which you really can expect as a maximum on the architecture. So how to run an Intel Advisor GPU roofline? So how to get insight into the maximums and how far you are away from this maximum? You have to do you have in the roofline analysis, you have to do it with the additional flags, or if you want to do it for the GPU with a profile GPU flag. And in principle, it is as with the roofline, with the advisor tool itself. You do have two steps. Yes, the first step is the so-called survey collection. In the survey, you collect timings, and therefore the advisor tries to run your executable which as less as overhead as possible. Yeah, so it's pure runtime taking. And the data is then collected in the project directory. And here I added only the search directory. In this slide, you see only that there's also a search directory added for the sources, for example. Just if you want to see it later in the, for example, also in the advisor GUI. And then this is very fast, the survey run. And then it's a much slower collection. This is the trip count run. And in the trip count run, you count the trip counts of your loops. You also count the flops. You do gather the stack information. And then, but it's very essential is that then the data is put into the identical directory from the survey run. So it's you have the same project directory. And then for the later analysis, both are combined. So you combine the timings from the first fast run with the exact numbers from the second run, from the trip count run. And then you get the then on this, the performance analysis, on this, based on this, the performance analysis done. You can also do the steps in one. There's also a minus collect roofline. This is I presented here also in 2 steps, because this is also what, if you have an MPI code, then is what you typically have to do, because if you do it with 1, the minus collect equal roofline, actually under the hood, it's still, these are still 2 runs. It's just for the convenience. And inside, it's still a survey run and a trip count run is done, and this cannot be executed under an MPI run execution, and therefore, if it's MPI run, with MPI, you have to split it into these 2 parts. Yeah, but finally, you can do this roofline report. Yeah, so you can either load it into a GUI, but you can also, again, as with the offload projection, you can also generate an HTML report, and the command is shown here. And by asking for a roofline report, but also you have to specify the GPU flag here, so that it is clear that you want to do it for GPU. Okay, so back to the demo, to the online demo. I go into the, now for the online demo, I have selected another already prepared code. So this is identical code which Heinrich used. Yeah, and this code is ready for execution on the GPU. I close this here, close this, close this. Yeah. Okay, so just to show that it's the same code here. Here we have the loop, and here is the queue submit. Yeah, this is the correct code. So the submission to the accelerator. Okay, so here here is again the JIT clone command where you can get it. So it's as Heinrich told it already. It's just in the one API samples, and then they're down into the hierarchy, and they're copied here in the next file directory. And it's done with a CMake. So the typical thing is here. Any question? Okay, I go there. I make directory, cd into the directory, CMake. Oh, this is small. Short and slow. And then I say Mike -J. If I put a verbose flag here, then it will show me all the commands. So I see here that the DPC++ compiler is loaded, is used, and then the -G flag is done. Okay. And then I do the, oh yeah, first I want to show you that it really runs on the GPU. Okay, we see here already that its performance is about 1.5 teraflops. And it selected here the level 0 drivers. It was executed on the ISXE Max graphics, so it's everything perfect as expected. In principle, I could also run it here on the CPU with this command, and let's do it just as an example. So this here, I select the CPU with OpenCL. And actually you have also here the about 1.1 teraflop. So it's very close to the OpenMP implementation. It's not identical code. The principal code is identical. Also, you see it from the file names. I think that the origin is identical, and you see that the is very close, and this gives really hope to the promise from SYCL that you can create a code which runs optimal on several platforms. Yes, perhaps you have to, from time to time, you have to do some additional tuning, but here for this example, for this compute-bound n-body code, it's very convincing for me. Okay, now let's do the roofline analysis. So first with this survey collection. So the overhead, you see it from the performance numbers, 1038 gigaflops, and before it was about before it was 1400. This is already a big difference, I would say 20% or so. Don't know the reason for this. And now we have to start the trip count analysis. It will take one and a half minute or so. So I will go back to the slides for this time and show you two additional slides about offload modeling, how to do GPU to GPU modeling. And here we have two different commands, two different slides for it. So this is the command line interface. So typically what you do on one GPU, you do some collection profile it there to first the service run, and then also you do the trip count run again with profile GPU. So this is exactly as before with the roof line, and then you have a third step then would be to do a projection, to specify here the parameter collect projection. And in this projection, you then also specify for which configuration, yes, for which architecture you want to do this projection. In our case, it's the same architecture. What I could go in principle, perhaps I'll do it if there's time enough. I can go back to the initial node. So this was the node without DG1 GPU, and do there the projection. But here it's a one-to-one projection. We took the data on the system and specify the same system. Yeah, all the steps, it's in principle also possible to do it just in one, and this is with the collect offload minus GPU and then the config. Yeah, this is just a combination of the three commands before. And here you see the alternative, how to do this with the Python scripts, just some other flags, and yeah, also possible. And you can also use the set parameter option as shown before to specify other specific values. So then you are not fixed to the defined GPUs here. Okay, back to the presentation. So here it ended in about 1.5 minutes. The trip count calculation, the trip count data collection was done. And then finally, I do create the roofline HTML file creation. Oh, it's in a level above. I know it's in build. Confused. It's built, and here the output I was done for to the in. I took the put the output directly into this directory here. Okay, and now here we see the roof line for this code, and obviously here this is a very perfect code because the peak performance is high, and also we see that it's very close to the architecture limits here. Perhaps one could still think about or look into the details whether it's possible whether all fused multiply and add instructions, which are in principle possible for this code, are also done. Yes, also done by the compiler, or if perhaps by some rearranging the code, more fused and multiply instruction could be generated. So this would be one option. So we are far away here from the bandwidth limitations. You see here the different values which were calculated by the small benchmarks in the beginning, the DRAM bandwidth, the GTI bandwidth, level 3, and SLM bandwidth. And yeah, here are the detailed numbers again, that here you could influence what you see. Also, red, yellow, and green, these are the different loops in the code, and you can influence the ranges here. So the red is not bad. Red just means it's a large loop. And also the circle here, the diameter is larger than for the green because these are just shorter loops. And shorter loops are, in the beginning, they are less interesting for doing any improvements and on any optimization. You will typically focus on the large loops because they dominate the execution time. Okay, yeah. Here is some, it's not showing in this. What you can also then do here, everything what you created on the, what you created on the dev cloud. So as I mentioned that the dev cloud is not possible, there are no GUIs. For Vitune, Heinrich showed you that it's possible to do a remote access with the Vitune tool itself. This is not yet implemented for the advisor, as far I don't know of it. And therefore, the different approach is then to download everything to a local machine where you have a GUI. And so I do this. I will download all the data to a local machine. And here I have opened a VNC connection so that I can start a GUI. So it has arrived. I go to build, advisor, and then I select directly the project here. Project. So the GUI will start, and here I show result. Do a new analysis. Okay, and now I have even more control about what I can see here. Yes, and in the GUI itself. I also could start here a new survey, new characterization. For example, if I want to go for another machine here, the performance modeling is done below here. There's no available GPU. Okay, I wanted to deselect some flags, forgot it. Can I think rely on the current data? They're not available here. Okay. I didn't test this before. I just wanted to show you that you can download the data and then go through this data with just a normal advisor GUI. Okay, a final step then was what I wanted to show you was the GPU to GPU. And when I go into this playbook here, I prepared here the command. Because we have run this on the GPU, and now I do a GPU to GPU projection. Actually, in principle, it should be identical numbers because it is on the same system. But this didn't show. This doesn't come out in the end. So here's a report generated. And the report of the projection is more optimistic as a real run. It says there should be still an still an improvement, and this is not realistic. So I will check with the developer. So whether it might be I did something wrong here. Yeah. Okay, and finally I find here a lot of links to resources for this work here. Also another example, the ISO 3DFD OpenMP example might be interesting. This and other material to the tools itself. So this, in principle, will end my talk. Are there any questions up to now? If not, we have the opportunity. I can do a recap of the roofline model, this final 5 minutes, or we make a larger break. What do you think, Edmund?
Yeah, I think we're fine when we're through. I mean, I don't think it needs to be artificially being extended. So yeah, definitely let's go into a bio break.